Modeling and control of voltage source inverter with current control using alpha, beta and DQ reference frames. So we are modeling the voltage source inverter using average model. Why to go with average model means PWM inverter switches at high frequencies, typically 5 to 20 kHz. The output voltage of one phase alters between plus VDC minus VDC by 2 during every switching cycle. Modeling every switching event makes it simultaneously slow, and analytical controller design is also complex. So instead we replace the switching waveform with its average value. So this is the average value taking over a one switching cycle like this. This is switching period TS. Switching period means 1 by switching frequency FSW, with which we are switching the PWM inverter. Now this is the average equivalent circuit of your inverter. Here plus, actually VDC is conveniently taken as plus VDC by 2 and minus VDC plus VDC by 2 for pole voltage analysis. VA is the pole of the inverter. If it is a three-phase inverter, we have VA, VP, VC, that is simplified as a single phase, considering single phase, and VA is the voltage with respect to DC neutral. So this is VA is plus VDC by 2 when switch is on, upper switch is on, and VA is called minus VDC by 2 when lower switch is on. So the average value is taken as VA is equal to duty D into VDC by 2 plus 1 minus D into minus VDC by 2, but D is a duty cycle, and VA can be reduced as 2D minus 1 into VDC by 2. So this is something like VA equal to M VDC by 2, what we have seen here. VA is AC voltage, M VDC by 2 is DC voltage. So this is reduced to MA is 2D minus 1. So D can be obtained in terms of the modulation index as 1 plus MA by 2. By controlling the modulation index MA, we can control the duty cycle. So these are represented in terms of voltage sources like this, and this modeling is called average model of a grid tied inverter, where VJ is the grid voltage, PDC is the DC voltage, PAC is the SZ voltage. We are averaging like this, x of t as 1 by ts or t to ts, t to t plus ts, x of t, where this x of t may be current or voltage over a one switching cycle ts. Average output voltage VA is MA into VDC by 2. So this MA equal to 1, this plus VDC by 2, and minus 1 minus VDC by 2, and so on. Now the source current ISA dash, when the upper switch is on, it is ISA, and lower switch is on, ISA dash. That is 1 minus D into IGA. If you substitute D as 1 plus MA by 2, you get 1 minus MA by 2. So the dynamic equations VA as LDA by dP plus RI plus VG. So VA is the inverter voltage and VG is the grid voltage, and grid voltage is considered as VA is equal to M VDC by 2. MA, so if you substitute this one here, then you will get this one. And if you write in terms of LDA by dt is equal to M VDC by 2 plus R minus RJ minus V. So the three-phase model can be obtained as like this: VA0, VB0, VC0, where VGA, VGB, VGC are grid voltages, VA, VB, VC0 are inverter voltages, and we can generalize like this. We call usually A, B, C are poles, so we write pole voltages LDA by dt plus RIG plus VA. This is the stress vector form, and by doing Clark's transformation, x alpha beta is equal to some transformation matrix T into x ABC. This is for ABC to alpha beta transformation. So this ABC voltage is what we have seen here. This is converted to alpha beta frame equations, where IG alpha beta is nothing but we have to write it as the individual equation like this: L di alpha by dt di beta by, actually this is something like a column matrix. So this is also a column matrix with M alpha and beta, Ig alpha Ig beta, and Vg alpha Vg beta. So applying Clark's transformation, x dq is equal to tp of theta x alpha beta, where tp of theta, this is to transform alpha beta reference to dq frame. So further the conversion matrix is like this. This we have already seen in the previous video of mathematical modeling of ABC to alpha beta frame and alpha beta to dq frame, how we got this matrices we discussed there. And here dIAG alpha beta by dt can be obtained as inverse transform of dq, or dq can be obtained as tp inverse tp times of dA alpha beta. So this is vice versa. Okay. So this Li alpha beta equation, if we consider, so this is required to do the controller design for alpha in alpha beta reference frame. This is required to design the controller in dq reference frame, where if you split this into dq column matrices, the first row is this one and second row is this one, that is igd by L igd by dt is equal to m bdc by 2 minus resistance drop and reactance drop, where this is called the coupling component. Means all these are d parameters, but it is dependent on q parameter, and all these are q parameters, and this is a d parameter, where this is nothing but a cross coupling. Okay. So one parameter on q is coupled with d in the d frame, and one parameter of d is coupled with q on the q frame. So the stationary frame control, alpha beta control, measures the current transformed into a stationary alpha beta frame. So here alpha beta are the sinusoidal quantities, whereas dq are not the sinusoidal quantities. So where alpha beta is like this, where this is the Vs, and Vs is operating at a frequency omega, where if this is the alpha beta frame, and this is the Vs, this is the dq reference frame, this is the q axis and this is d axis, and this is also rotating at angular frequency omega 1, this is rotating at angular frequency omega, where Vs is rotating at omega and the dq frame is rotating at a frequency of omega 1. Using PLL we have to make omega 1 equal to omega. So the measure currents transformed into the synchronous frame of reference, that is this omega 1, this is also rotating, so this is forced to rotate at a speed of Vs, so that we can capture the dynamics of the inverter in synchronism with the grid. So the appeared quantities d and q are pure DC, so we can control these two easily. Why we are doing these two in quadratic means, in quadrature, controlling one parameter will not affect the other parameter. Even in alpha beta or dq, we can control d and q individually. When you control d, it won't affect the q. There is no component vector on q. Means component vector of d and q is 0, component vector of q and d is 0. So these are purely decoupled. Now we can write the pole equations like this. So Vp naught equal to Vp naught into dq, Vp naught dq e power j theta. So this is the dq frame. So this represents these are rotating at an angle theta, means it is rotating at a some omega. So this is rotating at a, so Vg is rotating at a speed d phi by dt, and this is rotating at a speed d theta by dt. So these two speeds must be same. Okay. Now in this above equation theta equal to phi, in the above equation this means that this is achieved by PLL as we discussed, and where these two are cross coupled components, and this is the current controller design. See, this is the VGA of S, VG alpha of S, VG beta of S. This is obtained with the grid currents. This is obtained by comparing instantaneous grid alpha with the reference value, instantaneous grid beta with the reference value, and the error is processed with the PI controller, and it produces some control vector, control value U alpha, and this is compared with grid VG grid alpha through some feedback network. So this feedback component HFF is 1 usually in this video. So we can consider it as a low pass filter if we have some high frequency problem. We can use a low pass filter with whose function is omega base square plus omega square, or we can use a delay element e power from j theta. But here we are considering it as 1. I will show you the equations here. So M alpha can be taken as U alpha plus VG alpha into HFF. See this. So this is M alpha. This is considered as 2 by VDC times U alpha VG of alpha into H alpha. So where M beta is like this. So if you apply a closed loop control where this acts as a PI controller, and here U alpha, what we represented here, can be written as M VDC by 2 minus VGA. So this is the inverter voltage. This M VDC by 2 is VI, and this is VGA. So VI minus VGA can be considered as U alpha. This is the decided control output. So grid voltage minus inverter voltage can be considered as like this. With the feed forward, U alpha is V inverter minus V grid. Substituting these values here, V inverter minus V grid is considered as U alpha. Actually, this is the drop in the filter. That is V inverter minus V grid is drop in the filter. So this is considered as U alpha. This one. But what is U alpha here? U alpha plus VG alpha into HFF into 2 by VDC is MA. So you can keep U alpha here. But why we keep U alpha means this is the output of PI controller, and the same is the input of filter, L filter. So we can develop the block diagram like this, where this T of S is KPA plus KIA by S into LR. This is the open loop transfer function of this loop. U alpha and U beta are the control inputs and are manipulated as M alpha, M beta. So using these equations, we have obtained this one, where this feedback component is additionally added here to obtain this. So these are the equations. This we have already seen here. The same equations we are used here also. So based on that, the current control in DQ frame is modeled as like this. So this MVDC by 2 plus this component minus 2 by 3 VM. 2 by 3 VM is this one, this grid component gives rise to LS plus. If you bring this one to the side, LS plus R means we are converting this equation into Laplace. We can develop this part. So this will give us the current IGD. This is S L IGD of S plus R IGD of S is equal to M DC by 2 plus RI plus this one. Okay. So in the similar way, we model the bottom one also. This is the plant model for DQ current control. Now the control equations are obtained by choosing the control input UD and EQ such that they cancel out the disturbances. Means these are the disturbance terms. Okay. So we have to remove these disturbances by using some control input, by doing some closed loop control like this. Okay. Now rearranging the d-axis equations, it is like this for d-axis, where UD is this part. This is the drop in voltage. This is considered as UD. Then you can write the same equation like this: MD into VDC by T is equal to UD plus VGA minus this one. So in alpha beta frame, it is written like this: U alpha, U beta. But if you design in DQ frame, you will get this one. In DQ frame, we consider omega, this decoupled components. Okay. In alpha beta frame, we don't have that decoupled components, but in DQ frame only we get this decoupled components. In alpha beta, we are not considering the decoupled components. Here we don't have the decoupled components. So we don't have any cross coupling here, but we are taking the feedback signal from GSM. So TD can be written as the product of these two. Actually, this is DQ control, where this is alpha beta control. In alpha beta control, this is the TS. In DQ control, this is the TS. In DQ control, we have cross coupling components. In alpha beta, we don't have that. So in either cases, Kp by Kd is considered as L by R, and Kpd equal to L by R into Kid. Gc of S is equal to Kp plus Ki by S. So this is for the D axis, and Gp of S, that is the plant transfer function, is 1 by Ls plus R. So remaining under on either sides of the inverter, this is not something like a just a switch. So the plant transfer function we can consider as Ls plus R, and we are controlling this using a controller. Then open loop transfer function Gp Gc is obtained like this. Now the factor Kd equal to, so we can rearrange the same equation in this manner, and Ls plus R can be written as R times, if you take R outside, L by R into S, but L by R is here we write it as Kpd by Kid. So we can substitute somewhere here, where Gp Gc is Kd by Rs, what we have written here. If you take out Kp by Kd, so this is something like S plus 1 by Kpd by Kd into S plus 1. If you take Kpd as common, then divided by S into So this L by R is KPD by KID. I am taking it as L by R plus 1 into RS. So this L by R is KPD by KID. So this is KPD by KID into S plus 1, KPD plus KID into S plus 1. These two get cancelled. Then we will get this one, KPD KID by RS. So this is KID. This KID by RS we will get. So finally, if we take a closed loop transformation G by 1 plus G, so this is KD by RS by 1 plus KD by S, where G is GP into GD. G is equal to GP into GC. That is G by 1 plus G is closed loop transformation. That is this one, and this can be modified as like this. RS by KD, if you take outside, this KD numerator not cancel, then you will get like this. Then this is in the form of 1 by 1 plus S tau, where tau I is R by KID. So this tau I, that is the time constant tau I, is considered as R by KD, and GC is, that is controller transfer function, is GD star by GD by GD star. See, this is the controller transfer function. So this is the output and this is the input for this. So this is the closed loop transfer function. So this is, now let us suppose L is equal to 5 millihenry and R equal to 0.2. Usually this omega C taken as omega S by 10. Omega C taken as omega S by 10, and FC is taken as Fs by 10. This is the crossover frequency for this bandwidth. For easy control, we have to take 10 times below the switching frequency. So we got the cutoff frequency FC. It is estimated as 3142. Using this, Kp is L omega C. That is L we consider it as 0.005, omega C is we got, then we got Kp as 15.71. So Ki can be obtained from this relation R omega C. Or we can take this relation KPD equal to KID into L by R. We know L and we know R. Here using this we can estimate KID equal to R by Ti, where Ti is obtained or considered like this. Here KID, you can say this as KID is equal to R into omega C. Omega C we know what is omega C. Actually, if you take the time constant, we can model this in the time constant form. If you consider this time constant as one value, then you can model it in the time constant form. Or if you take a bandwidth in terms of switching frequency, we can model it in bandwidth form. Usually we prefer to go with this bandwidth form. The switching frequency is known. Usually switching frequency is taken as 5 kHz, so FC crossover frequency we can consider it as a 1/10 of that, that is 500 Hz. Then we can write like this. So from that we can obtain Ki value, that is R into omega C. So using this Ki we can consider Kp value by just substituting here. We get Kp and Ki values. We know that P is 3 by 2 times of Vd into Id plus Vq into Iq, and Q is VQID minus VDIQ times 3 by 2. So this negative indicates it is drawing power from the grid, reactive power from the grid, and it is pumping active power into the grid. So if the requirement is to inject the known amount of active power and reactive power into the grid, then once we write ID and IQ as like this. Thank you.